Okay, so we would like to prove that the set of rational numbers is in one-to-one correspondence with the set of integers. Now, this on the face of it seems impossible because of the following. Let's write down the first few integers. 0, 1, 2, 3, 4, 5, and 6, and so on. So the point about this is that there's a clear starting point and then the next point to go to, namely 1. But let's think about the rationals. We clearly can begin from 0. But what do I write down next? You see, supposing I write down 1/2. Well, that clearly is not the next number, because before 1/2 we have 1/3. Well, is that the next number? Well, no, because we have 1/4. And much before that we have 1 over 1 million. And so it seems as though there's an infinite set of rationals between 0 and 1/2, and in fact between 0 and 1/3, and between 0 and 1/4. So it seems impossible to write down a list of rational numbers. But in fact this is possible. And in fact the whole idea of proving that these two sets of infinite sets are in fact the same is to produce in a clever way this list of rationals. So how do we produce this list? Well, we'll do the following. I am going to write down on the first row 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and 1 over 6, and so on. On the second row, I'll write down 2 over 1, 2 over 2, 2 over 3, 2 over 4, 2 over 5. This will not go on forever, I promise. 2 over 6. And third row, I'm going to write down 3 over 1, 3 over 3, 3 over 4, 3 over 5, 3 over 6, and last row, I promise. Okay, so I claim that on this table we have all the rationals. It's an infinite table. So where would we find, let's say, 11 over 9? So we have 11 over 9 here. So we would go to the 11th row and to the 9th column. Where would we find another weirder fraction? Let's say 5692 over 63. Well, we would go to the 5692 row on the 63rd column. So in fact, all the rationals are on this table. Now, I still have not produced this list. I need to produce this list. You see, because it seems impossible. Because if I go across this row, it's infinite. So I'll never get down to the second row. And similarly, if I go down this first column, it's infinite and I'll never get to the second column. So I need to find some clever way of going across this table in such a way that I get all the elements of this table. And I'm going to do that by doing the following. I'm going to change colors to blue. I'm going to first do this. I'll go from 1 over 1 to 1 over 2, then from 1 over 2 to 2 over 1, then to 3 over 1, then from 2 over 2 to that, and then 1/3 to 1/4, 2/3 to 3 over 2, and then 4 over 1, and so on. So going down diagonally going down this table diagonally, I'll be able to get every element on this table. And therefore I can produce a list by unraveling this blue chain. So let's do that. So the first point in my blue chain was 1 over 1. Then the next was 1/2. Sorry. And the next was 2 over 1. Then the next was 3 over 1. And the next was 2 over 2, then 1/3. 2 over 2, then 1/3, then 1/4. Now there's a slight drawback to doing things this way. You see, here I have 2 over 2. But 2 over 2 is in fact 1 over 1. And at some point I'll reach 2 over 4, which will in fact be 1/2. So there are repetitions in this list. So I'm going to do one more step. I'm going to rewrite the list but remove the repetitions. So I'm going to produce a better list that is 1 over 1, 1/2, 2 over 1, 3 over 1. 2 over 2 I leave out, and I have 1/3 and 1/4. And this has all the rationals. It has all the rationals because it came from the first list, and the first list came from the first table, and we argued that the table had all the rationals. Now, there are better ways of listing the rationals in such a way that we can produce all the rationals once and only once, and only in reduced form. But the other way of doing things, called the tree of rationals, is a bit more complicated and will require that you take more of my claims on faith, because I will not prove them. But anyways, so we have this list. So how do we produce our map to the integers? Well, the first number, 1 over 1, will be mapped. I'll change colors to 1. 1 over 2 will be mapped to 2. 2 over 1 will be mapped to 3. And 3 over 1 will be mapped to 4. 1 over 3 will be mapped to 5. 1 over 4 will be mapped to 6, and so on. And this has all the integers. And there we have it. We have produced our magical map that has the mapping we desire. So we have found a way of listing all the rationals and listing all the integers and finding a pairing. So in fact, the set of all the rationals is in fact the same set in terms of its size as the set of all the integers. To use the math jargon, the two sets have the same cardinality. Okay, now let's show that the set of real numbers is in fact greater than the set of rationals or integers. In other words, that the infinity corresponding to the reals is greater than the infinity of the rationals or integers. Let's change colors again. Back to black. So how do we do this? We're going to, this time, prove this claim by contradiction. So this is a theorem. Set of real numbers is not countable. And the idea is that we will pretend we have this list and show that in fact there exists a real number that is not on the list, but that is nevertheless a real number. And therefore, any countable list that you can provide of real numbers, we will provide a mechanism to produce another real number that is not on the list. And this will show that the set of real numbers is not countable. Okay, so how do we do this? We will, so sketch of proof. So the sketch of proof. We'll pretend we have this list. So the first number will be A1, and so remember we're going to stick with the interval between 0 and 1 to make our lives easy. And A1 will be equal to 0 point. The first digit will be called D11. Second digit will be D2. D12, D13, D14. So this is 0 point something, and I'm just calling the digits after the decimal point these letters D11, D12, D13, D14. And the second number in our list will be D21. We'll have the decimal representation D21, D22, D23, D24, and so on. The third will be A3, which will be D31, D32, D33, D34, and so on. So what we've done, and this goes on forever. Okay, so this list is countable because we can list it with the integers, and we're saying that it has the real numbers that we desire. But this will be a contradiction because we're going to be able to produce another number. We'll call it B, and this time we'll use the color red because it's a special number. That will be a real number, but will be provably not on this infinite countable list. So we'll write down B, and this will be equal to 0 point because it's between 0 and 1. And how do we choose its digits? Well, we'll have to be clever about this. Well, I want to choose the first digit to be C11. Well, what is C11? I don't know. I don't care what C11 is, but my only condition on C11 is that it's not equal to D11. That's all I require. And what is the second digit after the decimal point for for B? Well, it's C22. Well, what is C22? I don't know and I don't care, but it's not equal to D22. What is the third digit after the decimal point for B? Well, it's going to be C33. Well, what is it? Is it 4, 5, 6, 7? I don't know. I don't care. But it's not equal to D33. And so on. We'll choose C44. What is it? I don't know. I don't care. It's not equal to D44. That's all I require. And this will go on. So the claim is that this number B is a very special number. It's not on our list. So not on list. How do we say that? Well, consider the following. Look at A1. Can B be A1? Well, it can't be A1 because A1 has D11 after the decimal point, but B has C11, which was by construction not equal to D11. Can B be equal to A2? Well, it can't be A2 because A2 for its second digit after the decimal point has D22, but we chose C22 in such a way that it's not equal to D22. Can B be A3? Well, it can't be A3 because on the third place after the decimal point, we have C33, which by construction is not equal to D33. Can B be A4? Well, it can't be A4 because A4 for the fourth position after the decimal point has D44, and we chose C44 in such a way that it's not equal to D44. So in fact, on our countable list for the real numbers, there exists a real number B that is not on that list. So what we've done is we've shown that given any countable list, because remember we did not specify what the numbers are. The numbers could be incredibly arbitrary. We don't know if they're rational, we don't know if they're whole numbers, we don't know if they're irrational or rational or transcendental. That list of real numbers does not have B, and therefore the set of real numbers is much, much, much greater than the set of the rationals or the integers. So the real numbers are not countable. And that's the proof that the set of real numbers has a larger cardinality than the set of rationals. There are other infinities that are greater than the real numbers, but that will take us far afield. And thanks for watching.